Okay, well this video is going to cover what was version 1 of the polynomial test of Unit 2 Part 1. So let's go ahead and just get right to it. The first set we need to factor completely. The first step of factoring is to look for a common factor. I see that both of these are divisible by 2. So if I pull out that 2, I can see what's left. So that's going to leave x to the third power minus 27. Remember, when you pull out a common factor like this, you are dividing. Alright, so those 2's cancel. That gives me x to the third power. 54 divided by 2 is 27. Hopefully you will look at this and notice that this is the difference of two perfect cubes. 27 is a perfect cube because it is 3 to the third power. Now, I had encouraged you to take your calculator and create this list down the side of your paper or on scratch paper by doing 1 to the third power, 2 to the third power, 3 to the third power. Just in case you didn't have it memorized yet. And then you would notice that 27 is a perfect cube, so you're on your way. Once you realize that you have the difference of two perfect cubes, then you have to remember the pattern. Alright, so the pattern worked like this. First of all, we're going to keep that 2. Alright, so I'm just going to put that 2 out front, and that's going to stay there. Now focus on this part. Alright, this is the part that I'm doing now. The sum or difference of two cubes always factors as a binomial times a trinomial. Okay, that's a 2-piece times a 3-piece. The binomial is just the root of these two things. Okay, so if I take this and I take this, alright, x to the third power comes from x. I keep the same sign here. 27, as we mentioned, comes from 3 to the third power. So the root of 27 is 3, the cube root. Alright, so we've got that. Just for fun, I should go ahead and mention to you that if you wanted to avoid doing the whole making a list thing, your calculator will do the cube root. You know what, I'm not 100% you'll be allowed to use this calculator, but in case you are, and I hope you are, you can do the cube root by typing in the number 3 and then doing second and this button. That makes it the cube root of whatever you type in. So that's another way. That's another way of discovering that the cube root of 27 is 3, right? Or you could just do the list. Anyway, you've got your binomial. It came from these two. Now your trinomial. Your trinomial is going to have a beginning, a middle, and an end. The beginning comes from squaring this. So square this, you get x squared. Okay, the end comes from squaring this. Square this, you get positive 9. That's always positive. Now the middle comes from multiplying these two terms together. Alright, it's always going to be the opposite sign. So this is negative, so I know it's going to be positive. And then 3 times x is 3x. So that's it. Alright, that should be your answer to number 1. Let me clean this up a little bit. Okay, take a look at number 2. Again, the first step of factoring is look for a common factor. Alright, in this case, the greatest common factor is 2x squared. Both terms have at least 2 x's, so I will pull out 2x squared. And then I will see what's left on the inside. Again, to see what's going on the inside, I divide by the GCF. So I'm going to divide both of these by 2x squared. The 2's would cancel, alright, and that's just going to leave x. Alright, I'm going to have minus 8 divided by 2 is 4. the x squares would completely cancel out. So that's it. There's nothing else I can do with this. This isn't squared or anything, so I can't factor this any further. So this is actually the answer. So you know what, I'm just going to drag it over here. Okay, put it on the answer line. So boom, there you go. Let's move on to number 3. This, hopefully you recognize this as the difference of two perfect squares. So we're just going to immediately factor that with very little thought, using the pattern that we've memorized. Alright, when you've got the difference of two squares, it always splits right down the middle. So 9x squared is definitely going to be 3x and 3x. It's always going to be plus and minus, and again 4 splits right down the middle, so this is going to be 2y and 2y. Alright, so boom, that's it. There's nothing else I can do with that. So this again is the answer. So I'm just going to drag this over and put it on the line there. Okay, so that was the answer number 3. Okay. For the following quadratics, solve using the method indicated. Got to show your work. Alright, for this one we are supposed to complete the square. Alright, completing the square involves a very special number being right here, and this is not it. So we are going to add 8 to both sides. Alright, that's going to give us x squared plus 4x, leave a space, is equal to 8. Alright, because those canceled out. Now we're going to complete the square with that special number that comes from doing half of the middle squared. Half of 4 is 2. 2 squared is 4. Okay, so I'll do plus 4. If I add 4 on the left, I've got to add it on the right. So this will always factor now as the same thing twice. Okay, so x squared, that'll be x times x. 4 will be 2 times 2. Alright, plus and plus. And of course this is 12. The benefit of having the same thing twice is that I can now write this as x plus 2 squared equals 12. Alright, now because I have something squared, I can unsquare it by doing the square root. Don't forget the solution will be plus or minus. Anytime you take the square root of both sides, you've got to put a plus or minus. Okay, so let's move this over. So the radical will unsquare this. So then I will have x plus 2 equals plus or minus. Now the square root of 12 is going to be 2 root 3. Okay, but this is what you might see, alright? 2 root 3. Whoops, wrong thing. Okay, so instead of plus or minus radical 12, we have plus or minus 2 root 3. Now we need to just subtract 2 from both sides, being careful to put it in front. And that really is going to be our final answer, so I'm going to go ahead and put it here. X equals, x equals negative 2 plus or minus 2 root 3. Okay, number 5. This one we are supposed to solve by factoring. Okay, so let's factor this. Yeah, so 2x squared, we look at that first. That will only factor as 2x and x, so done deal. Looking at the 35, 35 can only be 5, well, okay, it could be 5 times 7, or technically it could be 1 times 35. But, you know, most likely it's going to be the 5 and the 7. Now, it might be 5, 7, or it could be 7, 5. The way we know which one it is we check the whole the inner plus the outer has to equal the middle. So inner, I have 5x. Outer, and I'm multiplying here, I have 14x. I'm trying to get a 3 out of this, and all I can control are the signs. There's no way I'm going to get a 3x out of 5x and 14x. So this is not working. So maybe it's the other way around. So let's try 7 and 5. Okay, in that case, inner I have 7x, outer I have 10x. And again, I'm trying to get positive 3. I can do that. If I have a negative 7 and a positive 10, that will make a positive 3 answer. Okay, so that means negative 7 is right there, and the positive 10 would come from this being positive because we're talking outer. One last thing I have to check. Does negative 7 times positive 5 give me negative 35? Yes, negative times a positive is negative. So there I've factored it. Okay, once you have it factored, you don't stop because this is an equation and we are supposed to be solving, alright? The directions say solve. Solve means find what x is. Alright, if we were just supposed to factor and stop, the directions would just say factor like this, where it says factor completely. Notice up here we just factored and stopped. Factor completely. But down here we are solving. These are equations, so we keep going. The way we keep going is by setting these factors equal to 0 and solving. So we're going to be doing 2x minus 7 equals 0, and we're going to be doing x plus 5 equals 0. On this end, if I add 7 to both sides, I get 2x equals negative 7. If I then divide both sides by 2, like so, then I get x is equal to negative 7 over 2. So that is one answer. Meanwhile, I will subtract 5 from both sides. So that will give me x equals negative 5. So these are the two solutions. So negative 7 over 2 or negative 5. Okay. Now, number 6, we're supposed to factor using the quadratic formula. Alright, let us remember that the quadratic formula says if we have an equation that's in the form, let's see, ax squared plus bx plus c equals 0, then we could find the solution by doing this: opposite of b plus or minus square root b squared minus 4ac all over 2a. And you had to memorize this. It helped to know the song. Opposite of b plus or minus square root b squared minus 4ac b squared minus 4ac all over 2a, all over 2a. Yeah, learn the song. What? Don't mock me. Don't hate, don't judge. Anyway, this is the quadratic formula, and that's what we're supposed to be using for this problem. Now, this is not quite in standard form. Alright, for standard form, we need everything on the left except for equals 0 on the right. So basically, this negative 5 needs to get to the left. Yeah, get. Yeah, arrow. So we're going to accomplish that by adding 5 to both sides. So this is going to become 2x squared minus 8x plus 5, you see, equals 0. Okay, that means that a is 2, b is negative 8, and c is 5 in terms of plugging into our quadratic formula. Now, whenever you do the quadratic formula, I want you to calculate the discriminant separately. Oh, you forgot what the discriminant was. Is that what I hear you saying? Well, the discriminant is this part in here. Okay, all of this. That's the discriminant. You know, it probably would have been easier to do something like this. Bam. Alright, now that would temporarily block it out. But, you know, anyway, you get it. B squared minus 4ac. Do that part first. That's a discriminant. So, I think I'm going to do this in a different color. So our discriminant, you know, our b squared minus 4ac is, so that's negative 8 squared minus 4 times 2 times 5. So let's see what that is. Alright, negative 8 squared, that's positive 64. And I encourage you to type positive 64 instead of trying to write negative 8 squared down. Just do that part in your head. So there's my b squared minus 4ac. Okay, so that is 24. So our discriminant is 24. Always calculate that first. Now we can go on with the rest of the problem. Okay, so according to the quadratic formula, we need opposite of b plus or minus square root. So opposite of b is negative 8, so the opposite of b is going to be positive 8 plus or minus square root. Now the discriminant goes onto the square root all over 2a. Well, a is 2, so 2a is 4. So boom, this is where we should be starting out. Do not type this whole thing into your calculator. The only thing that you should be putting in your calculator is the square root of 24. And that's if you can't do it in your head, like I can. Alright, no time to teach you that right now. So, square root of 24 is 2 radical 6. Alright, so then this becomes x equals 8 plus or minus 2 root 6 over 4. Now this is essentially the answer, except for you should always look to see if you can reduce these three numbers. Now it's got to be all three or nothing. Now one of my students tells me that, well, I say one of my students, but one of the students who I help, who is actually somebody else's student, says that her teacher has them put a heart around these three to remind them that it's all about these three numbers. The radical 6 has nothing to do with it, and it's all or nothing. If there's a common number that you can divide all three of these by, do it. If it's just 2 of them and not the third, forget it. All of these are divisible by 2, so we should do that. We must do that. Okay, so we'll divide the heart by 2. I like the heart thing. And once we do that, that should be the final answer. So I'm going to move into position over here to put my final answer down. So that 8 I'm dividing by 2, so I'm going to have 4 plus or minus. Now these 2's sort of cancel out. 2 divided by 2 is 1. So I'm just going to put radical 6. And 4 divided by 2 is 2. So there you go. That's your final answer. Okay, please understand this is really 2 solutions. This is really, I think I'll do this in gray. This really means 4 plus radical 6 divided by 2, or 4 minus radical 6 divided by 2. That's what it really means, but you can leave it like the blue. Okay, let's take a look at number 7. Solve and graph, solve the inequality and graph the solution on a number line. Okay, inequality, C is greater than or equal to 0. The best thing to do is to solve this using factoring. Alright, so in fact for a minute I'm going to ignore the fact that this is actually an inequality, and I'm going to factor it and set it equal to 0. That way I'm getting the x-intercepts. So x squared is going to be x times x. 12, alright, slow down. 12 is either going to be 3 times 4, or 2 times 6, or 1 times 12. Alright, I'm just going to go in that order. So, well, no, I'm not. I'm going to look at the 4. Because there's no number in the front, you know, the leading coefficient is 1. I can immediately look at these and look for the one that could give me 4. So 2 and 6. Okay, I need a positive 4. So a negative 2 and a positive 6 will give me a positive 4. So boom, there you go. Now, to get the x-intercepts, I would set these equal to 0. So x minus 2 equals 0. And x plus 6 equals 0. Adding 2 to both sides gives me x equals 2. Subtracting 6 from both sides gives me x equals negative 6. Okay, so what I have here are the x-intercepts. 2 and negative 6. I'm going to go ahead and put those two on my number line. So really the negative 6 goes over here, and the 2 goes over here. Alright, boom, number line. Now, in reality, we're trying to find out where the function is greater than or equal to 0. So what we're going to have to do is pick some test values, one in each one of these zones. Alright, we have a zone over here, a zone in the middle, and a zone on the right. So you can pick any number you want. Now in this zone, let's see, I've got negative 6, so I could pick negative 7, negative 8, negative 9, anything like that, anything in this area. I think I'll go ahead and pick negative 8. Okay, will be my test value there. Now in here, I love to pick 0 for a test value because it makes the calculations easier. And 0 is definitely between negative 6 and positive 2. Let's see, now over here, I could pick I could pick 3 or 4 or 5. You know, anything, I could pick 100. But I'm going to go ahead and pick 4. So you pick whichever values you want to test, but you're going to need one in each zone. Now, I like to stay organized, sort of like this. I make a little table for myself. Okay, and you know what, maybe I'll just even do it just like this. Okay, so in this area I will calculate with negative 8, and here I'll do 0, and over here I will do the 4. So let's see, now remember, what I'm dealing with is this x minus 2 and x plus 6. Okay, so I'm dealing with, let's do the negative 8 first. Alright, so what I want to see is, if I put in negative 8, I want to see if it makes a true statement. And I'm shooting for this to be greater than or equal to 0. Okay, so if I put in negative 8 for the x's, that makes this negative 8 minus 2 and negative 8 plus 6. Alright, I'm just putting in negative 8 here and here. Alright, but it's got to be, I'm looking to see if the value is greater than or equal to 0, just like this. In fact, maybe I'll just change this back. Greater than or equal to 0. Okay, so is it yes or no? So let's keep going. So negative 8 minus 2, that's negative 10. And negative 8 plus 6, that is negative 2. Okay, so I'm trying to find out, is that greater than or equal to 0? Well, a negative times a negative is a positive, so in the end, I get 20. Is that greater than or equal to 0? Well, yes. Yes, it is. Okay, alright, I'm going to come back to that. But for now, I know that with negative 8, I get a true statement. So that tells me that this zone is going to be a zone of solutions. Now, what about the middle zone? If I put in 0 instead, then I get this, 0 minus 2. I'm just putting 0 where the negative 8 was. And I'm going to get 0 plus 6. And I'm trying to see, is that greater than or equal to 0? Well, that's going to give me negative 2 and 6. Is that greater than or equal to 0? Well, that's going to give me negative 12, right? Is that greater than or equal to 0? Question mark. Answer, no. That's a negative value. Negative numbers are not greater than 0. They're less than 0. So that's a no. Okay, finally we will test the 4 out. So if I put the 4 in there, it's going to look like this. 4 minus 2 and 4 plus 6. Trying to see, is that greater than or equal to 0? Well, that's going to give me 2 and 10. And you can already see that this is going to be greater than 0. That's going to give me 20 greater than or equal to 0. Just like before. Look at that. So that's, again, definitely a yes. So our test values tell us the places where we got a true statement, where you see these yeses, that's where the solutions are. So that tells us we will have solutions in the first area and the third part of the graph, but not in the middle. Now let's talk about the points themselves, the x-intercepts themselves. Let's talk about negative 6 and 2. Well, in this case, we were looking for values that were greater than or equal to 0. Equal to 0 is fine. And these values themselves are the x-intercepts. They are designed to give us a value that is equal to 0. So we will include these in the solution set. The fact that it's or equal to is a big hint that this is going to be a closed circle. So we'll have closed circles at the x-intercepts, and we will draw arrows like this to show that we have solutions here and we have solutions here. And we'll just leave this empty to show that we don't have solutions in this area. That was a no. Alright, so there's your graph. Now, you know what, maybe I'll move these down here, because unless you're watching the video, it looks like this is part of the number line, and it really isn't. Okay, can I erase? Okay, so there is the graph of the solution. Now, the solutions themselves, we will go ahead and use interval notation. To capture this part of it, this starting from the end, this is negative infinity. So we have negative infinity and then all the way up to 6. And we will use a closed bracket to show that we're including this endpoint. And then we'll have to put a union because we have these two separate pieces. And then we will say starting with the 2 and include that 2, and it goes all the way to positive infinity. Okay, this is the solution and this is the graph. Okay. Alright, let's talk about this graph. Now, please understand that the idea is that this goes forever in this direction. Okay, and this also continues forever like so. It doesn't stop. It just runs off the graph. Now with that in mind, the domain is the x values of a function, alright? All the input values, the x values. So graphically, it's how far to the left and right it goes, left to right. But since this graph goes left and right forever, we will say that the domain is negative infinity to positive infinity. Okay, now the range. The range is the y values of a function. So in this case, graphically we're talking about how low it goes to how high it goes. Now, the bottom of this graph, the lowest point is here. Now, we're going to need these decimals to help us know exactly how low that is. Which one of these numbers is telling me how low this is? It's this number right here. Okay, the y value is telling me the height. Alright, the x value is telling me how far over I am, and that's not what I need right now. So I'm looking at that negative 6.25. That's how low it goes. And then how high it goes, well, it goes forever. So the range is going to go from negative 6.25 to infinity, bottom to top. It has to be in that order. Okay, so negative 6.25 to infinity. Alright, and we will include the negative 6.25 with a bracket. Now, end behavior. Alright, in words, end behavior is all about what's happening on the left side of the graph and what's happening on the right side of the graph, looking at the ends, right? That's why they call it end behavior. So in words, we would say it like this. We'd say on the left, and the idea is, does it rise or fall? Alright, well on the left, it rises. Alright, it's going up. What about on the right? Well, on the right, it also rises. Alright, it's pointing up on both sides. So on the left, it rises, and on the right, it rises. Okay, so it's just a matter of turning that into math symbols. Okay, now the way we say on the left is we say as x approaches negative infinity, and that makes sense, doesn't it? Because negative infinity is over here. It's on the left. Okay. So as x approaches negative infinity, that means we're heading to the left. So then what happens as x approaches negative infinity? Okay, and we say f of x approaches. Alright, so far everything I've written, that part never changes. Okay, this means on the left, the function, and it either rises or falls, or occasionally there's an asymptote, but that's another, we'll talk about that another time. Well, it rises, alright, the function goes up and up and up. So how do we show that? We say it approaches positive infinity. So this is a symbolic way of saying on the left, the function rises. As x approaches negative infinity, the function approaches positive infinity. Now, I want to say on the right, it falls. Okay, well if this is the left, okay, this is how you say on the right. You say as x approaches positive infinity, and again you say what happens to the function. Alright, if it rises, we say positive infinity. If it falls, we say negative infinity. Alright, we already saw that on the right it rises, so we will again put positive infinity. Okay, on the left it rises, positive infinity. On the right it rises, positive infinity. Alright, that's how you do end behavior. Okay, in most cases that we're dealing with at this point, all of this is going to stay the same. It's just if it rises, it'll be positive infinity, and if it falls, you'll put a negative infinity. Anyway, the x-intercepts. When we talk about x-intercepts and y-intercepts, we are talking about points, ordered pairs. The x-intercepts are the points where the graph touches the x-axis. Let's see. There are 1, 2, 3, 4 x-intercepts. Alright, x-intercepts are always something comma 0. So what we have, this one right here is -8 comma 0. And then this one here is, what's that, -5 comma 0. And this one is 1 comma 0. And this one is 8 comma 0. Those are the 4 x-intercepts, the 4 spots where the graph touches the x-axis. So I'm just going to recopy what I just said. Alright, and again, an x-intercept is an ordered pair, so don't just put a number, put the whole thing, including the parentheses and the comma 0 and everything. Okay, now the y-intercept, and yeah, there's only one of them for this problem. The y-intercept is going to be, let's see, I think I'll do it in green. The y-intercept is right here. Now, to me, this looks like a decimal. It seems to be a little bit above 1. So, you know, it's something like maybe 1.3 comma 0. I'm estimating, and you know, I would give you anything between 1 and 1.5. Alright, so the y-intercept is approximately 0 comma 1.3. Whoa, I messed up the order when I wrote it down, didn't I? Yeah, yeah. A little embarrassing. Okay, yeah, it's on the y-axis, so we're talking 0 comma 1.3. Get it right, Burton, get it right. All right, it is time to talk about the absolute maximum. I think I shall use red. Now, for the absolute maximum, that would be the highest point on the entire graph. But as indicated by this arrow and this arrow, the graph goes up forever. So there is no highest point on this graph. So for absolute maximum, we will simply say none. There is no absolute maximum. There's no ceiling. It goes up forever. Absolute minimum would be the absolute lowest point on this graph. Does this graph have a lowest point? Well, yeah, the lowest point on this graph is right about here. In fact, it's labeled as 5.5 comma -6.5. This is the lowest point on the graph, so that makes it the absolute minimum. So we will put 5.5 comma -6.25 down as the answer. Now, a relative maximum would be a point that is at the top of its own little hill, but is not the highest point on the overall graph. And I see a hill right here. So the point at the top of this hill would be a relative maximum, because it's at the top of its hill, but as you can see, it's not the highest point on the graph because it keeps going up on the ends. So we have a relative maximum at -2 comma 2 as labeled. A relative minimum would be a point that's at the bottom of a valley, at the bottom of a dip, that's not the lowest point on the whole graph. That would make it the absolute minimum. But so here we have a point that's at the bottom of this dip, but it is not the lowest point on the whole graph. So instead of the absolute minimum, we call a point like this a relative minimum. So there is a relative minimum at -7, -1. Okay, that was easy peasy lemon squeezy. Now, most people got that stuff right. Some of the problems began to happen when we talk about intervals of increasing and intervals of decreasing. The key thing that you have to keep in mind is that these intervals are x values. X values, not y values. Most of my students could easily tell me, as we are traveling from left to right, sometimes we're going downhill and sometimes we're going uphill. So as I move this way across the page, but yet traveling on the curve like this across the page, I start off here at -infinity. Alright, and I'm calling this -infinity because I'm beginning here from the left. Alright, ignore the fact that it's pointing upward. We're only talking about x value, so up, down, that's irrelevant. The fact is we're starting here from the extreme left. That's -infinity. So starting from -infinity, we're going downhill, 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 downhill until we get to this point. And then it switches, and then suddenly we find ourselves going uphill for a while. Uphill, uphill, uphill. Alright, until we get to that point. And then things change again, and once again we find ourselves going downhill for a while. Downhill, 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 till we get to the bottom of that dip. And then one more time we find ourselves going uphill, uphill, uphill. Okay, and then we keep on going on up forever. So everywhere we were going downhill is going to show us a decreasing interval if we look at the x values. And everywhere we're going uphill will be an increasing interval looking at the x values again. So decreasing red, increasing green. So let's see, we're supposed to start with the intervals of increasing, so these two green intervals. Now just looking at the x values, alright, you see this increasing interval, but just look at the x values. Okay, this interval starts here and ends here. Okay, so x value wise, that is from -7 to -2. Okay, so we have an increasing interval from -7 to -2. Now look at this increasing interval, this other green. It starts here. You see it has an x value of 5.5. So it starts here, and you know, because of this arrow, it's here to remind you that this keeps on going forever to the right. Alright, so it starts here at 5.5, but then it never ends. This graph continues to drift to the right forever. So for that reason, we have to call it 5.5 to infinity. So these are the two increasing intervals. You might wonder why I'm using round parentheses instead of square brackets as we often do. Well, the red part is decreasing and the green part is increasing, but right at the bottom of this dip, it's neither increasing nor decreasing. Alright, at the very bottom, for an instant, it's flat. So we use the round parentheses to show that we are not including -7 itself as in the increasing or the decreasing. Alright, everything between -7 and -2 is increasing. But right at -7, it's not increasing or decreasing. It's right in the middle, and it's neither. Same with at the very top of the hill. It stops increasing here for an instant, it's neither increasing nor decreasing. So round shows not to include the endpoints. Anyway, for the decreasing intervals now, so switching to red, I already mentioned that we're starting here from negative infinity. Okay, so we're coming in from negative infinity because it goes to the left forever, and then we are coming up from negative infinity to here, x value wise. That's negative infinity to negative 7. Okay, if you were tempted to say something about negative 1, the mistake you're making is you're looking at the y value. But these intervals are strictly x values, so negative infinity to negative 7. So that's my first decreasing interval, negative infinity to negative 7. And then the other one is this red, which starts right here, okay, x value wise, and it ends right here. Okay, so from here to here, beginning to end. Now please don't say 2 to negative 6.25. These are y values. Again, we're supposed to be only doing x values, so instead you say here to here, negative 2 to 5.5. So that's the other decreasing interval, negative 2 to 5.5. Okay, that is how you do that. All right. I gotta change the my ink. Get ready for this next task. Rewrite the following quadratic equation in vertex form. Vertex form looks like this. Okay, it's this form. It has parentheses squared in it, and the bottom line is that we're going to have to complete the square. Complete the square. Alright, that's how you convert from standard form, which is what this is, into vertex form like this. So let's complete the square. In order to complete the square, this 49 is going to have to go away. I better zoom in. Okay, so I'm going to have to subtract this 49 from both sides. So that is going to give me y minus 49 is equal to 3x squared minus 24x. Now comes the first common mistake that students will make. We are not going to complete the square yet. In other words, I'm not going to take half of the 24 and square it and get 144. The reason is because of this 3. Alright, before you can complete the square, you have to factor out this leading coefficient, like this. So I'm going to have y minus 49, okay, equals, but before I can complete the square, I'm going to put this 3 outside of parentheses. Alright, so then I'll have x squared minus, if you're not sure what to put next, just understand that when you factor out a common factor, you divide. So you see I'm going to have negative 24 divided by 3. That's why I'm going to have negative 8x right here. Okay, just think about the distributive property. If I did the distributive property and multiplied again, I would get my 3x squared and I would get my negative 24x back. Alright, now is when you complete the square, once the 3 is outside of here. So now looking at the 8, I do half of the middle squared. So half of 8 is 4. 4 squared is 16. So I will put a plus 16 right here. Now here comes the other common mistake. A lot of kids will think I will do plus 16 over here. But that would be wrong because of this 3. This looks like a 16, but it's really what's going on here is 3 times 16. Imagine doing the distributive property. Right here I would have 3 times 16, which is 48. Okay, so this thing that looks like a 16 is really a 48 because of the distributive property. So I added 16 right here, looked like a 16. It's really 3 times 16. So to balance it out, I'm going to have to put plus 48 over here. So just remember, if there's a number outside the parentheses, I have to multiply it first, and that's what I have to put on the other side of the equation. In this case, 48. So if I add these together, oh, I'm sorry, negative 49 plus 48, well, that's just negative 1. So what I have here is y minus 1 equals 3 times. Now, the point of completing the square was to make sure this would factor as the same thing twice. So this is going to factor as x minus 4, x minus 4. Okay? So I'm going to go ahead and bring this over here. So now I've got y minus 1 equals 3 times. Since this is the same thing twice, I can go ahead and write it as x minus 4 squared, like that. But now I just need to get y by itself. So one more step, I will add 1 to both sides. So that is going to give me y equals 3 times x minus 4 squared plus 1. And this, my friends, is vertex form. And that's all you were asked for. If I had asked you for the vertex, you should have been ready to tell me that the vertex, and I'm putting it in gray like this because you weren't asked for it, but the vertex is the opposite of this, comma that. So the vertex would have been 4, comma 1, and you even should have been able to tell me the axis of symmetry, which would be x equals 4, always the same as that. Now, if you're studying for a recovery test, on the recovery test, I am likely to ask you what the vertex is and what the axis of symmetry is. So that's another reason why I'm showing you this here in gray. Alright, anyways, moving on. Now, most people did a pretty good job on number 10. We're supposed to sketch the graph that meets these criteria. So, we need a graph that has a range of negative infinity to 5. Okay? That means we need a graph that's pointing downward. You know, whatever else it's doing this kind of a thing. Okay? Because it's got to go from negative infinity, and then it has to go up to a height of 5. So negative infinity to 5. Okay, so just in the back of your mind, based on that alone, alright, and I can erase, so, you know, just, you shouldn't have a pencil in your hand while you're watching this anyway. So you just observe and then go back and do this on your own. But if the range is going to be negative infinity to 5, then that means there should be a ceiling of 5. The graph should not go above this. So, you know, so something that went like this, for example, boom. This would have a range of negative infinity to 5, for example. But let's see what else we got. But the graph is supposed to have a relative maximum at negative 6, comma 2. And a relative minimum at negative 2, comma negative 1. Okay. So, alright, keeping in mind that this green line here is the ceiling. Alright, keeping that in mind, we're supposed to have a relative maximum at negative 6, comma 2. So negative 6, comma 2 would be right here. This is supposed to be a relative max. So this should be like the top of its own little hill. Alright, I didn't do a great job on that. Let's see if I can do a little bit better. I said this should be the top of its own little hill. Okay? And then there's supposed to be a relative minimum at -2, -1. So this right here should be the bottom of its own little dip. Okay, so there should be a little hill here and a little dip here, because this is supposed to be a relative minimum. Okay, so let's see if we can make all this happen in what we have so far. So there has to be a little hill here, but then this green line right here, remember, this is the range goes up to here, which is good because this is only supposed to be the relative max, not the highest point on the graph. So the highest point will come up and hit this range that goes up to 5. So let's see what we have so far. So basically we could just connect these together. Okay, do something like that. And then this could go on ahead and come up and hit our range here. And so it's probably going to come back down. And those are all the instructions we have so far. So I could just go ahead and make this come on down. Okay, so far so good. The graph I've drawn has a range from -infinity to 5, just like we wanted. It has a relative maximum here at -6, 2. It has a relative minimum at -2, -1. Okay, and what else does it say? Alright, the end behavior is supposed to be on the left, it's supposed to go, it's supposed to fall, and on the right it's supposed to fall. Well, that kind of had to happen anyway, by following the other instructions, but sure enough, it is falling on the left and falling on the right. So we've taken care of that last criterion also. So there you go. This graph satisfies all of the criteria that we were asked for. So that's the best way to do it. Boom, something that looks very much like that. Okay, that was number 10. Alright, now number 11. You're just supposed to graph this, alright? Most kids did a pretty good job on this. You really should put the vertex right in the middle of your table. And as I mentioned before, the vertex, because this is vertex form, you understand, the vertex is going to be the opposite of this, comma, that. So the opposite of this will be +5, comma, then this stays the same. So 5, 3 should be the vertex. So we might as well go ahead and graph that. So there's 5, 3. This should be the vertex right here. The fact that this is negative means that we really are expecting an upside down graph like this. So just watch for that to happen. But anyway, the rest of this we can get by using our TI-30XS multiview. Okay, so you hit the table button on your calculator, and I see somebody's already been doing equations like this. And we're just going to type this in. This negative sign, make sure you use the white minus key. I saw a couple of kids trying to use the gray key for a negative sign. You don't want to use that in the very front. You're going to get an error message. So then the rest of it, x minus 5, so we'll do x minus 5, close the parentheses, square it, and then plus 3. So there it is, I've typed it in. If I hit enter, well, it's asking me where I want to start. So if I'm clever, I will think ahead. This is 5, 4, 3, and this is 5, 6, 7. So you see the graph is starting here at 3. Well, at least our table is starting here at 3. So I'm going to tell it to start at 3 for now. I'm just hitting enter a few times. So there you see we have 3. At 3 we've got -1, and then 2, and then 3. So there's my -1, and then my 2, and then the 3 that we predicted. Now, this is a parabola. It's supposed to have symmetry to it, balance. So we're expecting these numbers to repeat on the other side of the vertex. So I'm expecting it to go 2, -1 after this. But let's verify that by scrolling down. 2, -1. Whoops, went too far. Just like I thought. Well, heck, as long as we're here, notice that next is 8, -6. So for fun, I could put that down as well. And by the way, I could go the other way, again with the symmetry. So this should be 2, -6. Alright, because why not? So I'm just going to graph all these points now. So 2, -6. Alright, 3, -1. 4, 2. And then everything repeats after that, like so. Alright, so we have a nice field of points. So your graph should have looked something like this. Okay, there it is. There it is. Alright, well, this says write a quadratic equation that has a maximum and zeros at here and here. Well, okay, so we need a quadratic equation, a quadratic function. If we want it to have a maximum, that means it needs to be upside down. Okay, I mean, we know quadratic means, you know, like if it were written out, it would have x squared as the highest exponent. It's a parabola. Quadratic is going to be a parabola. And if it's going to be a maximum, it has to be an upside down parabola, so that it has a high point. And if it's going to be upside down, then it would have to have a negative in the front. Okay, now as far as having these zeros, okay, that means we could get those x-intercept. You know, this is you know, we're looking for a function that would have x-intercepts that are, you know, like 3, 0 and -6, 0. Whoa, that's an ugly one. Try that again. And we know that we get these zeros by taking factors and setting them equal to 0. So in other words, we could have gotten this 0 of 3 from a factor of x minus 3. And we could have gotten this 0 of -6 from a factor of x plus 6. So if we have this function, then there you go. This would be an equation that would have a maximum because it's upside down, and it would have zeros at 3 and -6, because if I set these equal to 0 and solved, I would get 3 and -6. So boom, there's the answer. Now I could multiply this out, and I guess I will just for fun, but based on the directions, there's nothing saying I can't leave it in factored form. But if I did want to go ahead and do it, I'd have negative, and this would be x squared, see minus 3, positive 6, that would be plus 3, and then minus 18. And then if I distributed that negative sign, it would be negative x squared minus 3x plus 18. Alright, so either one of these forms would be a good example. Alright, on with the review questions. Find a plus b. Alright, well, a plus b, we're just going to add these. So negative, maybe I'll just do this off to the side. Negative 31 plus 10 is negative 21. Negative 24 plus 9, and so on. So we get negative 5, 20, and 38 by adding each pair of corresponding elements. So then you just look for which one of these is the answer, and I see that it is C is the one that matches. So the answer to 13 is in fact C. Okay, alright, given this, find negative 2a. Well, that's just taking each of these and multiplying by negative 2, man. Alright, so that should be 6 and 16 and 14 and negative 8. Alright, so where do you see that? 6, 16, 14, negative 8. Oh, look, there it is. So that is D. Alright, remember how you evaluate the determinant. It's going to always be the down diagonal minus the up diagonal. So in this case, down diagonal is 15, up diagonal is 10. So that's just going to be 5. Alright, so that's A. So there you go. Alright, so that was an easy little review. Now for the bonus, the area of a rectangle. We've got this expression for the area of a rectangle. Find the two binomials that could represent the length and width of the rectangle. Justify your answer. Well, the area of a rectangle is length times width. Okay, so if I were to, doesn't this remind you of factoring? So they're telling us that the area is 2x squared minus 7x plus 6. So if we factor that, then we're going to get a binomial times a binomial that could be the length and the width. So 2x squared could be, well, it can only be 2x times x. And then 6. 6 is either going to be 2 times 3 or 1 times 6. I'm going to go with the 2 and 3 first. I definitely won't put 2 here because that would make a common factor with this one, so I will try the 3, 2 option. Now inner, that gives me 3x, and outer, I have 4x. I'm trying to get negative 7 middle, so I would need a negative 3x and a negative 4x, which would give me this. And a negative times a negative is a positive, so that will make positive 6. So this is the factored form. So with that in mind, then these are the two binomials that that could represent the length and the width. That's it. Also, let me throw in that this expression, 2x minus 3, is always greater than the x minus 2. So this is would best represent the length, and this one would best represent the width. And, you know, for example, if we let x equal 5, then, for example, 2x minus 3 becomes 2 times 5 minus 3. So that's 10 minus 3, which is 7. And then if I look at the x minus 2 expression, then that's 5 minus 2, which is just 3. So this would, of course, be the length, and this would be the width. Okay, so the 2x minus 3 is always bigger, so length width. Alright, I hope this video has been helpful to you. Please make sure you, if you're studying for recovery or something like that, please make sure that you can do these problems on your own without watching a video or copying off of me. You know what I mean? Watch the video to learn how to do it, but then go back and try to do the problems by yourself and see if you can still do it like the next day. Alright, I will see you on the next video.